Welcome back to C++ Quant Dev Fundamentals. In the first video, we covered a little bit about STL fundamentals and then vectors. And in the next video, we looked at lists, why they are almost never used on hot paths, and yet why operations like splice still matter in very performance specific critical designs. In this video, let's talk about why uh, abstractions matter in low latency systems, what they hide, and what they cost at the hardware level, and why low latency systems are unusually strict about where abstractions are allowed and where they are not. If you want to understand why real world quant and trading code looks the way it does, this is a key piece of the puzzle. C++ is often defined as a zero cost abstraction language. That means if you don't use a feature, then you don't pay for it at runtime. However, this promise assumes that the cost of a feature is explicit and local. In low latency systems, that assumption breaks down. A low latency system is where one response should be so fast, often in microseconds or nanoseconds, and crucially, it must occur predictably. And predictability means that the same operation takes roughly the same amount of time it runs. Abstractions will hide details, the memory layout, ownership, allocation strategy, and control flow. In many applications, hiding these details is beneficial, but in low latency systems, those details directly determine performance. So the goal of this video is not to reject abstractions entirely, but to understand why abstractions stop being zero cost, and why low latency C++ systems deliberately remove them from their most critical code paths. So the first thing we need to know is low latency is not fast average. Okay, when people say that a system is fast, they usually means it's average latency. Latency simply means the time between input and output. Low latency systems do not optimize for averages. They optimize for tail latency, meaning uh, percentiles like P99 and P999. So 99% requests are faster than this latency. That means P99 latency. 99.9% requests are faster than this particular latency. So that's called P999 latency. Why is this important? Because the slowest requests often occur exactly when systems are under stress. That means like contentions or bursts or volatility. And another key metric in this is called jitter, which means variability in latency between runs. If the average latency is low, high jitter makes a system unpredictable. Finally, determinism means that the same input follows the same execution path and produces the same latency every time. Not same, but similar. Low latency engineering is all about eliminating variance and just not just making code faster. Modern CPUs are extraordinarily fast. Most arithmetic instructions complete well in under a nanosecond. But CPUs are constantly waiting on memory. Memory is organized into layers like L1 cache, which is smallest and fastest, then L2 cache, L3 cache, and then the main memory, which is the RAM. A cache miss occurs when data is not found in a fast cache and must be fetched from a lower layer. So you were assuming that the data will be found in the faster cache, but it suddenly went into the lower layer. One cache miss can cost tens or even hundreds of nanoseconds, which is far more than hundreds of CPU level instructions. And this means performance today is dominated by data movement, not computation. Where your data lives in the cache and how predictably you access it, that matters more than algorithmic cleverness. And this exactly is where abstractions begin to break down. So, an abstraction hides complexity behind a clean interface. Examples include like containers hiding the memory layout, or smart pointers which hide the ownership, or like virtual functions which hide the dispatch logic. At runtime, abstractions can introduce some sort of indirection, accessing data through pointers or references rather than directly. And that indirection leads to the pointer chasing or cache misses. or branch misprediction. So abstraction also hides memory allocation and deallocation, which can later trigger expensive and unpredictable behavior inside the allocators. So the most dangerous aspect is that these costs are invisible in the source code. They only appear later in tail latency and in jitter. Let's take a case study, for example, list. List is a linked list container as we discussed earlier, and linked list stores each element in a separate node, and each node contains pointers to other nodes. That means elements are scattered throughout memory. From an algorithmic perspective, list looks efficient, constant time insertion, constant time deletion. But from a hardware perspective, it is hostile because every traversal step, as we discussed in the last video, follows a pointer. So it's pointer chasing. And each pointer may land on a different cache line. The CPU cannot prefetch effectively. So this demonstrates a critical lesson that big O complexity does only describes algorithms. It does not describe how code behaves on the real hardware. So the big O that we usually do in data structures and algorithms is not a study of how the code is being accessed from the real hardware. And that is why STD vector usually wins, but it still bites. Because vector stores elements in contiguous memory, meaning one element directly follows the next and that follows the next and so on. So that layout aligns perfectly with the CPU behavior, where cache lines are fully utilized, memory access is predictable, hardware prefetching is working effectively. And prefetching means that the CPU guesses future memory accesses and loads data early. However, vector is not inherently deterministic. When it grows beyond the capacity, then it will call for reallocation as we saw earlier. And then that can also cause some large latency, unpredictable spikes. So low latency systems therefore treat vector growth as a controlled event every time. And capacity is reserved upfront using vector.reserve, and resizing on the hot paths is forbidden. But why the STL hides these costs? The STL is designed for general purpose programming. Its goals are like correctness, safety, reusability, as we saw in the first video. But to achieve this, STL will hide many details like allocator behavior, like capacity growth policy, like destruction timing, or like the memory access patterns. And this abstraction is a feature for most applications, but a liability for low latency systems. The STL assumes that the average case matters the most. But low latency systems always assume the worst case will eventually occur, and that must be controlled. So this fundamental mismatch between STL abstractions and the low latency expectations is what causes problems on the critical path. Now coming to hot path and cold path. A hot path is a code that runs extremely frequently, millions of times per second mostly. And examples include something like order matching or event processing or packet handling loops. A cold path is a code that runs lately, rarely, like startup, configuration, or some administrative operation. So overhead on the cold path is insignificant. Overhead on the hot path, which is done more times, is compounding rapidly. So low latency systems therefore isolate the hot path and keep it minimal, explicit, and predictable. Abstractions are allowed, even encouraged, outside the hot path, but aggressively minimized inside the hot path. In object-oriented layouts, data is grouped by object, known as array of structures. In structure of arrays layouts, data is grouped by field instead. For example, array of structures was grouped by object, but structure of arrays was grouped by field. So structure of arrays is a way to improve cache efficiency, memory bandwidth, and SIMD vectorization. So it may look less elegant, but it may make the memory access explicit and predictable. And low latency systems value that the most. They want to choose these data layouts that expose the hardware behavior, even if that sacrifices some amount of abstractions. And therefore, determinism actually beats elegance. Because if you bring everything together, right, predictability, stable execution, minimal variance, then abstractions are acceptable only if they do not introduce uncertainty on these issues. Hidden allocations, hidden branching, hidden memory access patterns, they all increase jitter and they are going to destroy that determinism. Which is why low latency C++ always looks low level and repetitive. That is not accidental, it is intentional. So the final takeaway is this, that in low latency systems, determinism is more valuable than elegant abstraction. Um, let's stop here, and in the next video, we will look into intrusive data structures and what intrusiveness really means when it shows up so often in low latency systems.